has done pretty fundamental work in the revealed preference tradition, based on the idea that exploring preferences of economic agents, exploring the idea that preferences of economic agents are revealed through their behavior in the market. If I have to cite one work, I would cite his monography with Chris on revealed preference theory, which is, I think, is still the best introduction to the area. This book builds on a number of impressive papers, and a favorite for me is the axiomatic structure of empirical content, which is not the most cited, but I think is super elegant piece, an insightful piece of research, really a model that I give to my students. The best titled paper, however, is not that, but Savage in the Market, which is a great paper too, but also has a great title. Federico has done important work in other areas, like matching, game theory, social interactions, and general equilibrium, which is nice given the name of the lecture. And Federico has been at Caltech since he's finishing his PhD at Berkeley, but I have heard he's returning to Berkeley. He's a fellow of the Econometric Society, the Economic Theory Society, etc., and many other honors. And he also has a last name that sometimes is very hard to pronounce for English speakers. So please, without any further, welcome Federico.
Thank you. Thank you so much, Cesar, for that introduction. And thank you for the organizers for inviting me to give this lecture, which is a great honor and a pleasure to be in Mexico City. Can you hear me? Yeah? So it's a paper that I wrote with Chris Chambers, like Cesar said, and it's a paper that we wanted to write in memory of Kim Border, and we like to think that this is a paper that touches on many of the topics and uses some of the techniques that Kim was very fond of and that he used himself in a lot of his work. So in particular, basic idea behind and the machinery that we use in this paper is also used in Kim's famous theorem, the Border's theorem in mechanism design. And we learned about this from him. So it was really important for us to write this paper and to remember Kim. Okay, so what's the paper about? So it's a paper about trying to do welfare economics in situations in which utilities are unknown, but where you have data on the past choices of the agents. And so we call this empirical welfare economics. Okay? But there's a caveat. This is theory. So there are parts of real preference theory that are relatively close to what you can do with data. And this is still, a step removed from what you can do with actual data. But we hope it is suggestive and that there is sort of there's a path towards completing those steps from this. And I think I know lots of people here are William students, so you're familiar with this. So Chris is a William student. So he told me about this quote, and I confirmed it with him yesterday. So I may be paraphrasing, but it's something like this. So when you face a model, the first thing you should do is understand its Pareto optimal outcomes. It's like brushing your teeth. Don't think about it, just do it, and you will never regret it. So we took this advice to heart here, and our main result is exactly about the Pareto optimal allocations in a very standard neoclassical allocation problem, where if we teach our students all the time how to understand the property of efficiency of Pareto optimality. We know it's given to us by, under the right assumptions, by equality of marginal rates of substitutions. And since I can't say marginal rates of substitution, I would say MRS in the rest of the talk. It's given to us by the equality of MRS. But of course, this property relies on having access to the agent's utility functions. So we're going to essentially solve the same exercise when you don't have access to the agent's utility functions, but instead you have data on the past choices of the agents. Okay? on the observed choices of the agents. Right? And I've noticed people in the conference, maybe because of the hybrid format, but they are very quiet and shy about asking questions. But I think that any talk is just more interesting if people ask questions. So feel free to ask questions. Yes?
Did you say you can work MRSs?
Marginal rate of substitution. It's a very difficult thing to pronounce. Okay, so here's an overview of our results. So first I will talk about a simplified version of the problem, a very simple warm-up question, but still interesting. So in this question, we're going to assume data on an individual agent's past consumption choices. And we're going to be given two new bundles, X bar and Y bar. And we're going to say, try to say when would the agent, when can we determine, based on what we know from the past actions of the agents, that they would prefer X bar over Y bar. So think about making a decision on behalf of an agent, or making a policy decision that's going to affect this agent, and that's going to determine whether they get to consume X bar or Y bar, where we can't ask this person what they want. We have to make a decision based on what we know about them from the past choices. So the idea that I will flesh out later is going to be quite simple. It's going to be based on, it's actually a little bit related to one of the papers yesterday. Yes, so Clemens represented. So it's going to be based on the convexity of preferences. I'm going to be able to exploit the convexity of preference in a very sort of standard way. So we have X bar here. I'm going to try to understand when I can say that X bar is preferred to Y bar based on the convexity of the preferences of these agents. And there's a property that, so when I teach this to the students, I call it the second welfare theorem for one consumer. So second welfare theorem for one consumer is that if you wanted to consume X bar, then you look at the upper contour sets given by the preferences, convex, and then you find the supporting hyperplane, that's just the line here that supports the upper contour sets at X bar. And this budget set that is defined by this line is going to be what that's going to be the budget that you need to give this agent if you want them to buy X bar, okay? So you can kind of decentralize this problem instead of feeding them X bar. I give them instead this budget set, and they will be happy to buy X bar. But the same observation tells me that if then by this, by this hypothetical, price, but this hypothetical budget, you can afford Y bar, then I can also infer that X bar must be better than Y bar. And that's the idea that we will exploit in this paper. The main result, like I said before, is going to be about efficiency. So this is a quick overview of the results. So given utility functions, we're going to look at when a system of equations characterizes Pareto optimal allocations when we start from consumer data. So what we'll basically reformulate the equality of MRS in terms of the revealed preference that are defined by the data. And the trick is going to be similar to this picture. It's going to be to find a common supporting price. It's not going to be a price that is observed, but we're going to ask ourselves, when can we find a common supporting price that supports the agent's consumption, all the agent's consumption, with the same price? And that property is exactly the property of equality of MRS. And we have a way of asking that question in the presence of consumer data instead of having access to the agent's utilities. And then once we have that formulation, we're going to be able to translate that property into a statement about something observable, about the real preference relations that are given to us by the data. Now, the same methodology is going to yield us answers to similar questions. So, for example, given a proposed aggregate change in the economy, when can the winners compensate the losers? So this is an idea that you're probably familiar with. It's called a color criterion. So it is a proposed policy change. For example, you open up the country to trade. Well, after you open up the country to trade, maybe it's possible for the people who lose by the policy change to compensate. So the people who win from the policy to compensate the losers, well, then this policy change is decidable. of course, as you know, there's a big discussion about this criterion, which we're not going to go into, but we're going to basically formulate this criterion in an empirical way, so based on this data from the consumers. Again, the same technique gives us gives us a way of answering many other related questions. So, for example, understanding empirically which allocations can be equal-ratio equilibrium allocations. So, give me an allocation when can we say, given what we know about the consumers, that there's a price for which this could be an equilibrium allocation, or similar, given a price vector. When can I say, given what I know about the consumers from their past choices, that there's an allocation for which this price constitutes a competitive equilibrium? Similarly, we're going to look at the existence of a representative consumer, but I think I will try to avoid getting to this in the talk because it's a little bit of a digression. Anyway, so let me go to the model. So the model is going to be very familiar to anyone who has studied reveal preference theory, but I just go over the model. It's a very simple model. So this model is really about consumer theory. So it's about neoclassical consumer theory. So you have a single consumer who's making a choice of a consumption bundle when they're facing a budget. So a pair, P and X, is an observation where P is a strictly positive vector in Rm and X is a non-negative vector in Rm. And you should interpret this as I observe the agent consuming or buying the bundle X when they were facing prices P, and where the budget they had to spend was exactly what they spent, okay? So the product PX is the budget that they had to spend, okay? And so we can talk about, whether that's, what that assumption means and what it does, but it is the way we always work in reveal preference theory. Now, a finite list of observations is a data set. So a finite list of observations KXK is an individual data set. And here we're going to talk about collective choice. So I have a finite set of agents, N. And so a group data set will be a collection of individual data sets, one for each consumer. Okay? So when I have a sub-index for each of these observations, that tells me the observation that corresponds to individual I. Okay? And here, I often get questions, well, what do you mean PKI? Why doesn't everyone observe the same prices? Well, if you want to impose that additional assumption, you can. There's no reason why you couldn't. But if you have access, if you have seen actual data, they often have different prices because, I go and observe, one consumer, bought something on this particular date from this particular supermarket, and then you go, you have data from another consumer who bought something on another date from another supermarket, and then and the prices are not identical. So this, unfortunately for us economists, the law of one price doesn't hold exactly. But also these observations could be done in sort of in asynchronous ways. The thing is, you just have data from these consumers, and there's no assumption about how this data was generated. Okay. Now, the standard question, the basic question in reveal preference theory, when you have an individual consumption data, is it rationalizable? So what does it mean? So an individual data is rationalizable if it is consistent with utility maximization. So in particular, if there is a utility that is maximized at each of these observations, given the budget that they have and given the prices that the consumer faced. Now, if I don't impose any discipline on the utility function, then of course anything is rationalizable because I can have a constant utility function, and then this question would never have any bite. So we impose some kind of discipline on the utility function, and usually the discipline we impose is local association. Here I will impose, actually for no particular reason, I will just impose a little bit more. I will impose that the utility function is strictly monotone increasing, or actually monotone increasing. So if y is greater than or equal than x, then utility of y must be greater than x. And if y is greater in every component than x, the utility of y must be strictly greater than utility of x. Okay, that's what I mean. But actually, we could do this with local association. This is just laziness on our part. There's nothing important about this. And so, when is a data set rationalizable? When there exists an increasing utility function such that if the utility of x is greater than the utility that I get when I consume the bundle that I consumed in the kth observation, then it must be that I couldn't afford x. Okay? So in other words, that by consumer xk, I maximize UI in the budget that the consumer faced. Okay? And then when this happens, we see that this utility rationalizes the individual data set. So an individual data set is rationalizable if there is increasing utility that rationalizes it, and a group data set is rationalizable if there is a utility for each of the agents that rationalize each of their choice. Okay? That's the, yeah. Oh, yes. Does that work? Yeah. All right. So, so I'm sure you have seen this, but how do we study this problem? And when we look at an individual consumer, and we do this through the real preference relation. So let me just remind you of what the real preference relation is. So we say that x is reveal preferred to y. So x squiggly ri y. If either x is equal to y, or if x is purchased at some observation, okay, and we could have afforded y. So that's the reveal preference relation. Now, there is a strict version of this. So we say that x is strictly reveal preferred to y if there is an observation in which I purchased x and I could have afforded y with some money left over. Okay? Now, the word strictly reveal preferred should suggest to you that something is revealed strictly preferred. So what do I mean by that? I mean that if you have in mind a utility function that is locally non-satiated or increasing, then if I could afford y with money left over, it means I could afford to buy something bigger than y with money left over. And so, I could, it means that x would have to be at least as good as that thing that is bigger than y, and therefore must be strictly better than y, okay? But that's a matter of interpretation. In any case, as for definitions, there's a binary relation which is called strict reveal preference, and x is strictly reveal preferred to y if this holds. Now, from this binary relation, I can take the transitive closure, and I will call that the indirect reveal preference relation. So I will say that x is indirectly reveal preferred to y if I can find a sequence of x, x1, x2, x3, all the way to xl and then y. So x is reveal preferred to x1, which is reveal preferred to x2, and so on, all the way to y. So if I have in the back of my mind a transitive relation, then I would have to conclude from this chain of real preference relation that x is better than y. And certainly when I look for a utility function that rationalizes, then it has to be that the utility of x is greater than the utility of y. Yes?
Yeah, so couldn't it happen that by this definition, x is strictly preferred to y and y is strictly preferred to x both?
Yeah, that could happen. Yeah. So when that happens, then the data is not rationalizable. Yes. But certainly there are data like that, yes. Yeah. So I will talk about that in a second. Now, the indirect revealed strict preference or indirect strict preference should be is when in this chain, in this sequence, at least one of the comparisons is strict. And then I will say that x is strictly or indirectly strictly referred to x, to y. Okay? So those are very standard definitions. And then we say that a data set satisfies GARP when there are no two x and y, so that x is reveal preferred, indirectly reveal preferred to y, while y is indirectly strictly reveal preferred to x. Okay? And this is something that is known to be inconsistent with a utility that rationalizes the data. So when this doesn't happen, then we see that the data satisfies the generalized axiom of reveal preference. So that's GARP for short. And it's, you're probably familiar with GARP or with SARP, the strong axiom of real preference. So strong axiom is the correct real preference axiom to study demand functions, and GARP is the right axiom to study demand correspondences. Okay, so here we look at correspondences, so that's why we look at GARP. Yeah. Now, the most important theorem in real preference theory is Alfred's theorem. So it's a beautiful thing. I always like to tell people about it, so take the chance to do it now. But also it will be important in this paper. So it's not just for my enjoyment. But it's a theorem about an individual data set. So take an individual data set, and then the following statements are equivalent. First is the data set is rationalizable. Okay, so remember this means that there is a utility function which is monotone increasing. You could take it to be locally unassociated, but monotone increasing. That is maximized at each of the observations. The second property is that the data set satisfies GARP. So these two statements are equivalent, and this is quite easy to show. Okay, so that these two things are equivalent. The next two are really sort of where the meat of this theorem lies, and it will be very important for our paper. The next two properties. So the next property looks maybe a bit mysterious, but it says there are numbers lambda k and uk, okay, for each observation. The lambda case must be positive, which satisfies these linear inequalities. So UL must be smaller than or equal than UK plus lambda k pk in a product with a difference in x's. Okay? So this may look mysterious if you haven't seen it before, but the way to explain where this comes from is comes from looking at the next property. So the next property says there's a strictly monotone increasing and concave rationalization. So this really is the punchline of this theorem. Okay? I start from only asking when the data set is rationalizable with a minimum discipline on the utility function. And that turns out to be equivalent to the existence of a very well-behaved utility function that rationalizes the data. One that is strictly increasing, which is good, but amazingly one that is concave. Okay, so you get a concave utility function in a sense for free. So either the data is not rationalizable at all, or it is rationalizable using a concave utility function, which is pretty remarkable. Now, in light of where we're going to arrive, we can now think about property 3. So what does property 3 mean? Well, remember, if you have a concave utility that rationalizes, imagine for a moment that this concave utility is also smooth. Then at each observation, you must have the first order condition has to be satisfied. So the gradient of utility, so remember when you solve consumer maximization problems, the gradient of utility is going to be equal to the Lagrange multiplier times the price, right? So look at this inequality in statement 3. You have the Lagrange multiplier, if you interpret lambda k as the Lagrange multiplier, times the price. So that's going to be the gradient of the utility. Then this inequality is the overestimation inequality of a concave function. So you have a concave function, you're standing at a point, x, you calculate, so you want this numbers u to be the number of utils. So you calculate how many utils you're getting at x, and you want to estimate how many utils you get at x scale using the gradient. Then by looking at the utility and then using the gradient to take the linear extrapolation to calculate how many utils you get at XL, if the function is concave, you will have overestimated. That's the defining property of a concave function. And that's exactly what this inequality is saying. Okay? So this inequality is, in a sense, encoding two things: the first order conditions and the concavity of the utility. Okay? So it's a little bit like us asking, okay, is there a concave function which takes the levels UKs at each observation that solves this maximization problem with this first order condition with the Lagrange multipliers or lambda. Okay? All right, so that's Alfred's theorem. So like I said, the proof that 1 is equivalent to 2 is simple. Of course, 4 implies 1. So, and it's relatively easy to show that 3 implies 4. So really the key in proving this theorem is to prove that 2 implies 3, okay? And that, I'm not gonna do that today, there are several proofs out there. But there's one which relies on the theorem of the alternative, on Farkas' lemma. And that's really the one that's going to be important for the talk today, okay? So if, I'm not going to go over this today, I don't have time, and it's relatively technical, but but basically our proofs will rely on tweaking the proof of Alfred's theorem that relies on the theorem of the alternative. Okay. All right, so let me go back to the Alice's, so that this kind of warm-up problem of, well, having a single consumer, and I'm going to call her Alice. So we have one consumer, okay, for now, for maybe 5 minutes, and we're going to have observed her past choices. We're going to have a data set about Alice's past consumption choices. But now we're faced with a choice that we have to make on her behalf. So we are given 2 bundles, X bar and Y bar, and we have to see if we can determine whether she would have preferred X bar or Y bar. So more precisely, I'm going to ask this particular version of the question. Given this data set, when can we say that the utility of X bar is greater than the utility of Y bar for all monotone and quasi-concave utilities that rationalize the data? Okay? I'm going to restrict attention to quasi-concave utility. I am kind of justified in doing that because Alfred's theorem tells me that if the data is at all rationalizable, it is rationalizable by a concave utility, so of course by a quasi-concave one. But then that serves as an excuse for me to just restrict the exercise to monotone and quasi-concave utilities. Okay? So we're not the first to look at this question. This is a question that is addressed in a paper by Halvarian in 1982. Actually, this is a beautiful paper that sort of popularized Alfred's theorem, because Alfred, despite his brilliance, did not write a very clear paper. And so a lot of people didn't know about this until Varian came along and wrote this really elegant paper that explains Alfred to the rest of us. And in this paper, in Econometrica 1982, he looks at this question about a single consumer and these 2 bundles, and when can you say that for this consumer, for any rationalizing and concave utility, actually, in Varian's case, can you say that one is better than the other? Okay? And he gives an answer, but it's not a very intuitive answer because he wrote down a linear program that if it has a solution, then the answer goes one way. If it doesn't have a solution, then the answer goes another way. And this is, of course, the type of thing that we know how to work with, that, you know, at least I learned from Kim, and that essentially if you work this out, then you will get an answer, and I'll tell you what the answer is. All right, so first, how would you think about this question if you hadn't read Varian's paper? Well, I think you would start thinking about something like this. No? So suppose first there's some observation at which you happen to have chosen X bar when Y bar was affordable. Well, then, you know, reveal preference theorem tells you that, you know, of course, then X bar is better than Y bar for any rationalizing utility. So then we have an answer, right? Okay. Second, you could use transitivity. If you have one observation at which X bar is chosen, and then some other observation is affordable, and some other observation is affordable on the second one, and another, and so on until you reach Y bar. Then again, by transitivity, of the real preference relation, I could conclude, well, since X bar is indirectly referred to Y, then I will conclude that X bar is better than Y bar for any rationalizing utility. Okay. Next, I could try to use monotonicity. So for example, if X bar is bigger than Xk, and Xk is revealed preferred to Y bar, then again I can conclude that X bar, for any monotone increasing rationalizing utility, must give Alice a higher utility at X bar than Y bar. But then, once I have monotonicity and I have transitivity, I can again go back and try to exploit the additional, I can take the transitive closure of the composition of monotonicity and transitivity and see how far I get. okay? And I can go on and see how many comparisons I can make in this way. But then I can also use convexity. So how do I use convexity? Well, imagine that X bar, I can write it as a convex combination of some bundles. And by the previous reasoning, I can determine that each of those previous bundles have to be better for Alice than Y bar. Then, by convexity of Alice's preferences, I would have to conclude that X bar is also better than Y bar. No? Because Alice has a convex upper contour set. So if I find a bunch of things which are in the upper contour set at Y, then the convex combination must also be there. Right? Well, then I have now a bunch of other comparisons that I can again go back and take the transitive closure of. Okay, so I could sort of iterate this procedure of using the three elements that I have, transitivity, monotonicity, and convexity, and then see how many comparisons I can complete. Okay, how much do I learn about Alice's choices from convexity, monotonicity, and transitivity, and the observation that I saw her make. So this might seem like a very complicated procedure. You could imagine write down an algorithm that you could carry out in this way, but it turns out that if you instead write down the Alfred variance LP and you work out the dual, you get a relatively simple answer. And here's the answer. So given a data set and two bundles X bar and Y bar, I will say that X bar bests Y bar if I can write X bar as a convex combination of bundles ZL. For each of those bundles ZL, there's some observation XK, so that either ZL is greater than or equal than XK, and XK is really preferred to X bar, or ZL is greater than or equal than XK, and XK is really preferred to Y bar. Okay? So basically, I'm saying that X bar, I can write as a convex combination of things which are either even better than X bar or better than Y bar, an occurrence of the latter. Okay? And it's strictly bested if it's weakly bested, and at least one of these binary relations has the strict version of it. Okay? And I guess I need to go a little bit faster. All right, so it's easy to see that when X bar bests Y bar, or strictly bested, then for any concave, actually quasi-concave and increasing rationalizing utility, the utility of X bar must be greater than utility of Y bar. So how do I know that? Well, because if I write, you can see this, right? So if I write it this way, I got pretty good at doing this on Zoom. Just by the quasi-concavity, I know that the utility of X bar is greater than the utility on this. Well, actually, let me do this for a concave utility. So we do this for a concave utility. So by concavity of the utility of X bar is greater than the convex combination of each of the utilities. And then I've determined that U is a rationalizing utility, and ZL is greater than UK for each one of them. So then this is worse. And then each of these is referred to either X bar or Y bar. So I can write down this convex combination as these two components, one for X bar and one for Y bar. And alpha must be strictly greater than 1 because I must have at least one occurrence of the latter. And one of these inequalities must be strict. So therefore, the whole inequality must be strict. Okay, so it's easy to see that this property is necessary. And I guess the important thing, the punchline is that this is also sufficient. And then you get a theorem that says for any data set, if X bar and Y bar are any two bundles, then the utility of X bar is strictly related to the Y bar for any concave and monotone rationalizing utility, if and only if X bar strictly bests Y bar. Okay. So this is sort of the kind of results that we're going to get in this paper. So I'm going to have to compare these two things based on the data I have, and in principle, you can think of some very complicated iterative procedure of using the data and using what I know about the preferences of these agents, over and over again to see what I can conclude and what I can't conclude. But there will be a relatively simple, and actually simpler than the one you have seen, way of just checking whether this holds or not for all rationalizing utility. Okay, so let me, I don't have time, so I can't talk about Bob for very much, but I will just talk about Bob to give you one definition, okay? So, because this definition is going to be the important one later. So this definition is called domination. So it's kind of like besting, but it's simpler than besting. So we say that a bundle Y weakly dominates X bar if it is a convex combination of bundles ZL, each of those bundles being revealed preferred to X bar. Okay? So it's simpler than besting. So Y weakly dominates X bar if I can write Y as a convex combination of bundles, each of which is revealed preferred to X bar. Okay? And Y strictly dominates X bar if it weakly dominates it, and moreover, in the defining convex combination, one of the comparisons is strict. Okay? And then I will skip this theorem, and I will go to the main result of the paper, which concerns many agents, not just one agent. Okay, so now we have many agents, so Alice, Bob, Carol, David, and when you have many agents, we can talk about allocations. So an allocation, it's a little bit confusing because allocation is usually allocation of something, but be patient and think of an allocation of just a specification of a consumption bundle for each of the agents in the economy. Okay, so one consumption bundle for Alice, one for Bob, one for Carol, one for David. Okay, that's an allocation. Now, here's something you're all very familiar with. So if I have utility functions for all these agents, I can talk about Pareto optimality. So we say that X is Pareto efficient for these utilities that I have for these agents if there's no other allocation, Y, which is an allocation of the same, so they add up to the same, right? So if I add up all the bundles for all the agents in X, and in Y, I get the same aggregate bundle. If all the agents weakly prefer what they get in Y over what they get in X, and one agent strictly prefers, okay, I'm sorry, I guess I'm defining this the other way around. So X is Pareto efficient if there's no allocation Y. Oh no, I am defining this inequality should go the other way, right? So if there's no allocation Y, which Pareto dominates it, okay? While the aggregate bundle on the Y is equal to the aggregate bundle on the X. Okay? I managed to mess up the simplest definition, but luckily you know this better than I do. Okay, when there's no such allocation, we say, when there is such an allocation Y, we say that Y Pareto dominates it. All right? Okay, so given that we know what Pareto domination means when we have these utility functions, now we can define what the empirical counterpart of this is. So here's the empirical counterpart. We set an allocation X is empirically Pareto efficient for a group data set if there exist rationalizing, increasing, and quasi-concave utilities for which X is Pareto optimal. Okay? So this is the question that we're going to talk about today. So give me an allocation X, and then you want to know when there are utility functions for these agents that rationalize the choices, are consistent with the choices, which are monotone increasing quasi-concave, and for which this resulting allocation is Pareto optimal. So it's an obvious caveat here. So first of all, I haven't asked about any monotone increasing utility function. I have restricted the whole exercise to convex preferences, okay, quasi-concave utilities. That's the first caveat. And the other one is that I only asking for one utility function for each of the agents that rationalize the choices and for which this is Pareto optimal. But maybe there are others that are also consistent with the data and for which this is no longer Pareto optimal, okay? But that's just the nature of the exercise. So when we reject it, then we are very confident that there are no utility functions, which are monotone increasing and quasi-concave, that are consistent with the data and for which this is Pareto optimal. When you don't reject, then you have this uncertainty that maybe, there are other utility functions for which this is, for which the answer would be different.
But you don't want to ask a question as to whether this calculation for all utility functions which would rationalize the individual choice. This could be another question.
It is a reasonable question that I don't know the answer to. Yeah. Notice for Alice, it went the other way around. For Alice, I could say for every rationalizing utility, x is better than y. But here, it's just the nature of quantified elimination that this works this way, doesn't work the other way. It's, yeah. Any other questions? Yeah.
So you would be sure that an allocation is inefficient. Would you be able to identify with certainty the Pareto optimality?
That's a good question. Yes, for each candidate utility. Yes. But the improvement may not be the same. Okay, so here's the answer. So the answer is an allocation y empirically dominates an allocation x if the aggregate bundle on the y is more than or equal than the aggregate bundle on the x. Okay, or if you want, you can take them to be equal, but just it's slightly easier to state the theorem this way. Each yi weakly dominates xi for each i. Remember what this means. It means that each yi can be written as a convex combination of bundles, each of which is indirectly preferred to xi, and strictly dominates it for at least one i. That's what it means for y to empirically dominate x. So the theorem says that an allocation is empirically Pareto efficient if and only if it's not empirically dominated. So basically, the statement of the theorem is sort of syntactically like the definition of Pareto optimality, but instead of a statement about utilities, what you need is a statement about these binary relations which are derived from the data, essentially exploiting monotonicity, transitivity, and convexity in the ways that I described before. Okay? But instead of being a definition, it's a theorem, because it requires that you actually show that the Pareto definition of Pareto optimality translates to this when you formulate it this way. And then let's see, let me just quickly mention, I think for this audience, Kaldor may be particularly interesting. So let me just mention the Kaldor criterion. It's not as elegant, but it's one of the things we can do. So let me just remind you of what the Kaldor criterion is. Now, again, just with Pareto optimality, I am just trying to think what the best thing to do with the time I have. But okay, let me just talk about Kaldor first quickly. So just like with Pareto optimality, I could tell you what Pareto optimality means if I have access to the utility functions. Let me just remind you of the Kaldor criterion when I have access to the utility functions. So suppose you have utilities for all the agents, and you have an allocation x, and you now have a proposed project that would change the aggregate consumption from the aggregate sum of xi's to z. Okay, so you're going to build, a new energy plant, or you're going to open up to trade or something like that. So you're going to have a collective change that's going to move the aggregate bundle that we are consuming as a collective in some direction. And we want to be able to determine whether this change is desirable. Okay? So there's actually a very practical way of doing this, which is cost-benefit analysis, there are lots of people doing this all the time. So and sort of the theoretical foundation behind it is this Kaldor criterion. So it rests on this idea that actually, let me draw you a picture. I have a picture here. So here's a picture. So this is an Edgeworth box. And so in this Edgeworth box, you have, I should do like this. This point here is aggregate consumption. So in this collective of two agents, that's what they're consuming in the aggregate, right? And how are they consuming it? Well, they have decentralized this consumption into this bundle for one agent, and then this other bundle for the other agent, which is upside down. Now I can look at the upper contour sets of each of these two agents, and it's an efficient allocation, no? Luckily. So there's a common supporting hyperplane, right? So here's a second welfare theorem, right? So this common efficient allocation can be decentralized as long as I give each of these agents these budgets that will be happy consuming what I want them to consume. Now, this agent who is facing the problem right side up like we are, that's the upper contour set. And the other agent is upside down. They have an upper contour set which looks like that. But imagine I turn it around and I represent this upper contour set in the same coordinate system as the first agent, and then I add them together. Okay? You add them together, you can add two convex sets, and you get another convex set. That's going to be everything that is to the northeast of this green contour. And this was actually mentioned by Mark the other day. This contour is a Skitowski contour. So what does this mean in economic terms? So everything that lies on the northeast of this green line are all the aggregate bundles that I can disaggregate in such a way as to make both of the agents better off. So if this policy change we're considering moves the economy, moves the aggregate consumption inside the Skitowski contour, then we know that there's a way of disaggregating after we made the policy change to make everyone better off. Okay? And when that happens, we say that the policy is desirable. And then it's and then we say that that this is the color criteria. No? So this is called cost-benefit analysis because if these are market prices, then the same market price will support the Skitowski contour, and then locally you can evaluate these changes using market prices. So this gives you a way of operationalizing this policy recommendation by cost-benefit analysis, by calculating the value of the aggregate change using market prices, and that's the way in which this is used in practice. All right. Anyway, so let me go back to. Right. So then, what we want to know is, I mean, all of this requires information on the utility function. So what can I say when instead of having access to utility function, I have data on the consumer's choices? So, okay, so I'm going to say that X weakly dominates an allocation Y if Y is not in a Skitowski contour of X. Okay, so when that happens, if you tell me that you want to change the economy from X to Y, then this tells me that that change is not desirable. All right, so here's a corollary. So now think of two allocations, X bar and Y bar. And X bar is where we are now, it's a status quo. And a policymaker or someone comes and asks you about whether Y bar is, should we move the economy towards Y bar instead? Now we don't have access to utilities, but we have access to a data set for each of the consumers. So the corollary says that if for any allocation, so it's a little bit messy to read, but it's actually not that bad. So remember that to be able to use the Skitowski contour in the way that I described before, you really have to think about local changes. So think of any local change in the direction of Y bar. So for any theta, I'm going to start from X bar, and I'm going to move the economy. I'm going to start at this aggregate bundle, and I'm going to move in the direction of Y. And you want to know whether this change puts us inside the Skitowski contour. So what can I do with that change? Well, I can achieve any aggregate bundle that, that doesn't involve more than that. So for any sort of candidate aggregate bundle set bar, if I can disaggregate it, giving each individual consumer a set bar, then it can't be that I can do this with goods left over and where someone gets something that is that dominates X1. Okay, when each of them weakly dominates. Okay, it's a little bit messy to state, but it is essentially the type of situation that we're in. We're talking about efficiency. So you look at the definition of the Calder criterion, and what you need is something that is sort of syntactically very similar, but where the role of utility functions is played by this relatively simple binary relations that you can infer from the data. Okay. All right, so I think I have 5 minutes. Yep. So in 5 minutes, let me tell you what the trick is here. So the way we address all of these questions, well, not the first question. The first question is using this Alfred variant LP, but all the other ones. So when you look at these Alfred inequalities, you can notice the following fact. I can pick one inequality and then set the lambda to be 1. So if you look at the system of linear inequalities, pick one observation, pick any solution, and take, let's say that observation is the kth observation, just divide everything by lambda k, and you have a solution to a problem where that lambda is 1, okay? But that allows me to look at this problem, where all the observations, except for the k at 1, are as before, and here, in the kth observation, I can have the price be an unknown and still have a linear system. So in Alfred's theorem, with Alfred's system of inequalities, I have a quadratic system. I have the lambdas multiplying the p's. So then, since I know the p's, the only unknowns are the lambdas, so I have a linear system. But here, I can pick one observation and be agnostic about the price, while maintaining the linearity of the system. And that's a trick we do. Since all of these questions are about the existence of some supporting price, we want to know when there exists such a supporting price. We translate all of these questions into whether there exists a price, but that's the trick. And since we only need to do it once, we can do it while the system remains linear. So you write down, you need to be very patient because it's a very big linear program. But conceptually, it's not very complicated. You just write down this linear program, and then you study the dual, okay, in ways that at least I learned from Kim, and you work the dual, you massage the dual until you get something. And when you're lucky, this dual gives you something nice, like it does in the theorem about Pareto Optimality. Some other times, it's not quite as nice. But in that particular case, it comes out to be something quite nice. And that's basically what we do in this paper, so that we look at a family of questions, all of which can be looked at using the same technique. By looking at the corresponding system of Alfred inequalities, we combine the data with some counterfactual observations or allocations or prices, and then we get this sort of expanded system of Alfred inequalities that remains linear because of this trick, and then we work through the dual until we get an answer. And that's basically the question. There's a lot of, there's very, very quickly, 1 minute. Of course, this is related to many related questions that have been studied in the literature. there are many people who have looked at counterfactual demands, started from variant, but there's a lot of people in sort of more applied area preference analysis in econometrics. Of course, there are people looking at equilibrium, market equilibrium from the area preference perspective. There are 2 papers by Bachmann, who also uses a very similar trick to what we have done here to address these questions. There are also many people who looked at aggregation problems from the area preference perspective. We're also looking at welfare and equilibrium and incomplete preferences, which has also been looked at by Gabriel and by other people. And of course, reveal preference and welfare is also an active area of research that a lot of people have looked at. So, I mean, what we have done is different from all of these papers, but it also touches on some of the same topics and ideas. And yeah, I'm out of time.
I was wondering about complexity. I mean, in some sense, if you have little data points, then complexity is not an issue, but then you don't have the information to estimate things. But, so my question is, if you have many data points, it seems to be complex to determine whether one allocation empirically dominates another one. Can you say something about complexity in the number of data?
In the number of data. It's polynomial in the number of data. Because it is ultimately an LP. So it is polynomial in the number of data. So each system of Alfred inequalities for each individual consumer, you have one inequality for each pair of observations, and you have 2 unknowns for each observation, and we're adding a counterfactual inequality for each individual agent. So it's a polynomial problem.
But at some point, you must determine whether something is a convex combination of the data, right? And this is still polynomial?
It is polynomial. That is not obvious, but it is. Yeah, thanks to duality, it is polynomial. Yes, it's a. That we haven't. That's a very good question. Yeah, and that we can study with similar techniques. So that's a very good idea. Yeah. Yeah. Yeah.
You thought of taking inspiration from William again, going beyond Pareto and asking about, for instance, ambiguousness. So the possibility of finding one rationalization that would get ambiguousness for the allocation.
Yes, thank you. We have actually, yes. So that's yeah. We hint at it in the paper. We suggest that you can do it with these techniques, but we didn't include in the paper. It's messy. Yeah, but but it can very much be done with the same techniques. Yeah. Yeah, so the result is like this. So of course aggregation is impossible. I don't need to tell this audience. Aggregation is not it's always difficult. And to get a representative consumer usually requires severely restricting the income distribution. Otherwise, you can only get it when the consumers are essentially the same and have homothetic preferences. So the name of the game is to restrict the income distribution. And so the exercise that we looked at here is rather different from this one, so that uses different ideas. But we ask, so suppose you have data about each individual agent, And suppose that the aggregate data is rationalizable. And then, in a sense, I can think of the aggregate data as then being generated by a representative consumer who has chosen the income distribution. So this is sort of Samuelsonian in a spirit. So, so if you endogenize the income distribution through a social welfare function, then you get this sort of representative consumer who is with its endogenous income distribution gets this. So we looked at this question when you want a utility function for each individual agent, utility function for the representative consumer that generates and explains the data, and moreover that counterfactually for all price vectors gives you a representative consumer once you endogenize the income distribution. But where I have the degree to endogenize to generate the income distribution for all the counterfactual observations, and that property turns out to be very weak. So there's only like a technical condition plus, rationalizability of the aggregate data that gives you this property. So in a sense, it's a lesson about how permissive this idea of endogenizing the income distribution is. That's reason. Yes.
When you have empirical Pareto efficiency, is it possible to try to find an upper bound on the possible inefficiency with the actual preferences? Something like the word coefficient would not be more than.
Maybe. Yeah, because it is certainly possible to work with a family of rationalizing utilities, at least to the extent that they can be parameterized by these coefficients you get from the Alfred equality. Yeah, we haven't thought about it, but yeah, it's possible.
Thank you all, and thank you, Federico. You can use the same techniques. The BCC, do other stuff. You can add other stuff. You see.